Okay. Hello and welcome everyone. Welcome to this lecture. Uh, till now, we have covered something called variational inference, and what we are, what we will see now from now on is basically something called variational autoencoder. In its true terms or in its true form, this is where the uh, this is where we actually start uh, with the modern deep. So whatever we call as modern deep generative modeling. Okay. So till now we have seen one form of generative modeling, which is this EM algorithm. However, for the first time we will see something which is more relevant and uh, yeah, I mean VAEs. I think is something that kicked off, all. So, in some sense, VAs act as the basis of the modern deep generative models, like whatever we see, diffusion models, stable diffusion, all of these things. They root from VAs, and VAs root from variational inference. So all of these things are connected, and yeah, yeah, we will see how all of these things are connected. Let me share my screen. All right. Okay. Cool. So. Let me create one more notebook. So this is the fifth one, right? So this is five variational auto encoders. Or these are also called auto encoding variational base. So then, yeah, whatever you would like to call it. So so this is let me write it down. So this is number five. It's called variational autoencoders. Okay. So, so let's take a step back. What was the whole idea of variational inference? The whole idea of variational inference was quite simple, that you want to maximize your elbow, which is a proxy for your log likelihood, so to say. And I mean, the one way to you maximize this elbow is using EM algorithm, but that requires you to find exact value of your uh, pz given x. And in simpler cases, this might be possible. You can calculate the value, the distribution p of z given x explicitly and use it for your, e step, m step, so on and so forth. Uh, but I mean, in complex cases, there is no tractable form of pz given x because of the intractable partition function that comes in, and yeah, we are stuck. And a solution to that, which is provided by this variational inference framework, is that, well, okay, you cannot set q of z to be equal to p of z given x. What you can do then is, well, you can restrict the class of functions. Uh, you can restrict q of z to a class of tractable distributions, basically, right? And then maximize L. And we saw one example of that, which is this mean field approximation or factorized approximation, where you assume that your q of z is actually a product of this qi of zi, where I goes from 1 to m. So you basically partition your zi into m disjoint groups, and you say that, well, the joint distribution is nothing but the product of these disjoint groups. So product of distributions of these disjoint groups. And then we simply saw that, so we saw how to maximize the elbow, and I mean, end of the day, we were able to find a closed form expressions of these distributions. And yeah, I mean, quite intriguing, right? Quite interesting that without doing anything, yeah. So let's see. I mean, yeah, it was quite intriguing that we were able to find closed form expressions of these distributions without, you know, and in a very quite straightforward manner, actually. So let's see how what we can do to, do something. Can we do something similar with variational autoencoders, right? Right. So let us first see that. So so before we start anything, let's look at two ways to write your elbow. Okay. So if you remember, so, so two ways to write elbow. What are these two ways? So now we will, so for from now on, let's represent elbow using this L function. Okay, we'll use L to denote elbow because it will be a loss function or something. So let us write it like that. Okay. Uh, okay. So hmm, how should I start? So before we get started, let us just write down elbow for a second. Okay. So so let's write down L. Uh, Maybe let me write it down as a function theta, L theta uh, of x. So what is this? If you remember, it was nothing but q of z, okay? Q of z log of p theta. I mean, again, we are now going back to our EM kind of notation where we had a theta, right? So this is the theta of x comma z divided by q of z dz. This is what our elbow looked like. Okay. Now, so use now as we saw that variational so I mean as is always the case uh in variational inference the core idea is that we will restrict Q of Z to a class of tractable distributions. Okay. The question is how do we do that? Well, the answer to that question is as follows. So what we will do is we will do the following approximation. So we will say that Q of Z. So in this entire VAE framework, we are going to make this uh, uh, you know what? Let me not confuse you. Let me write this as F only so that we will introduce L later on. So this is your F, your usual elbow. So so as I said, that variation inference will basically constrain the class of distributions that this Q can assume. So what is the approximation that we are going to do here? So this time what we will do is we will say that okay, actually this Q is approximated or constrained through this thing. So first of all we will introduce a parameter phi. Okay. I mean we will say that Q of Z is actually not is a parametric distribution. That's the first thing. Then what we are going to say is that, well, now this distribution is not just dependent on Z, it is also dependent on X. This is the variational approximation that we are going to make. I mean, remember that in mean field approximation, what we did was we said that Q of Z is this thing, right? I mean, yeah, quite a clever choice that, allows you to get individual forms of QIs particularly. However, in various VAEs, what we will do is that we will make this approximation instead, that Q of Z is this kind of distribution. That's all. Okay. So, okay, okay, fine. So, we will come to so what are we saying here? So actually, if you think about it, right? Uh, so so remember our PGM view, right? So this was the PGM that we were earlier looking at. So this was our generative generative view. Now, what variational inference has done is that it has made Z a function of, like, if you think about it from the perspective of a PGM, right? What variational inference has done, it has introduced one more node here and it has added this H. And this is your inference view, variational inference view, or it's just inference view. So if you want to infer Z, that you have to first get X. So if you have X, you can get if you have X, you can infer Z. And once you have Z, you can generate X. So you can think of this is like a new PGM now. Okay. Now, of course, one might think that, this is X, this is X, so this is actually a cycle. I mean, one can think of it like that, right? So one can think about this picture as you have Z, you have X, right? There is this thing and there is this thing. You can think that there is a cyclic thing, and in PGMs we discussed that, oh, we can only have a DAG structure on it and things like that. Well, we'll see that, this is not exactly true because, I mean, this is fine. I mean, there won't be any issues because we'll see that the function of each of these things is different. I mean, this generative view is something which will be sort of disjoint from the inference view. Okay, we will make sure of that. But however, we will learn it jointly. So I mean, we'll see what you will see. What do I mean by that? Okay. So I mean, the takeaway is that, well, we are going to use this approximation from now on. Okay. So, if you have this approximation, so let us in that case, what? So once you have that, so what will your elbow become now? So let's write down this L. So now you remember that you have two parameters. One was theta that was already here. And now we have introduced another parameter, which is phi. So now the elbow will become function of both theta and phi. Now I am representing elbow, so which is dependent on both theta and phi as by L, this calligraphic L. This is again a function of X. Okay. So what will this thing be? This thing is Q phi. So I'm just substituting this approximation here. Okay. This will be Q phi Z given X log of P theta of X comma Z divided by Q phi of Z given X dz, right? So this is what this is our this is our yeah. I hope there's no issue with this, right? If you want to write it, another way to write this thing is as expected value of under Q phi of log of P theta of X comma Z minus log of Q log of Q phi of Z given X, right? So this is one way to write it. So this is one way to write it. Okay. There is another way to write the same elbow. Okay. So if you remember from our very earlier result that your elbow is actually this thing, right? So your elbow is actually nothing but your log minus the scale divergence. You can write this thing as down. So you can use this to write the elbow in another form as well. Let me write that down. So uh, again, your L theta comma phi of x is, if you remember, so that the first term was log of p theta of x. So this is your usual log likelihood, nothing fancy, minus dkl of q phi of the earlier it was just z, but now we have substituted it with q phi z given x, scale divergence with this, and p theta of z given x. This was already there, right? This is what it is. Uh, okay, right. So I want to basically write this thing in a separate form. Let me try and write that thing down. This is log of mm, I want q phi z given x. Uh, hmm. Okay, let us write it down. Mm, should I write it like that or okay, let us write it down. Log p theta x minus expected value under q phi, right? What is this thing? Log of q phi z given x minus log of p theta z given x, right? Uh, if I just do some manipulations here, uh, so if I take the whole expectation q phi, right, this is just a constant, so I can take it inside the expectation. It won't affect anything. Uh, so that will become log of p theta of x. Take the minus side inside, so that will make it log of p theta of z given x, right? And minus log of q phi of z given x, right? This is what it will become. Uh, what I should do here is that I will okay, so what I will do is I will add and subtract something. I will add p theta of z and subtract p theta of z. So I'm just adding and subtracting this term. Let me let me color code this. Okay. Where is it? Sorry. Color. Yeah. So I have just added and subtracted this term. What this thing will do is it will give us another form to write it down. So it will become q phi of. So let us club these three terms, right? So we will club these three terms. So this is log of what? P theta of x, p theta of z given x divided by, sorry. Oh, sorry. Hmm, maybe I'll just change the colors. So this is actually opposite. This is minus, this is plus. Um, yeah, minus will take it to denominator. This will become p theta of z, right? And then minus, let's take this minus and then p, sorry, so the numerator will be still q phi of z given x divided by p theta of z, right? So I have clubbed these two terms and these two terms. That's all. So I mean, nothing fancy, right? I have taken this inside the expectation as this doesn't depend on z at all. So this will just come here. Take negative side inside. This will become plus. This will become minus, right? and then add subtract this p theta z term, combine these three, combine these two, this is what you will get. So this thing, so this is actually expected value under q phi of what? So this distribution, what is this distribution? So the above two, these two will make it p theta of x comma z, right? The joint distribution, and divided by p theta of z, right? So what will this thing become? So this thing, if you remember, is quite simple. This is nothing but log of, so just use Bayes rule, right? So this is actually p theta of x given z, right? Minus uh, yeah, expected value of q phi log of z, log of q phi of z given x divided by p theta of z, right? So if I have to write this thing right, finally this thing will become q phi of z given x. So you first take expectation under q phi z given x of ln of p theta of x given z minus. So this thing is nothing but your KL divergence dKL between what? Between q phi of z given x and p theta of z. So if you have to think about it, so these are the two terms, right? So there was one way to write it down, which is this way, right? Which is actually useful in EM and mean field approximation, right? So I mean there are two ways to write the elbow. The first way is this thing which is used in EM and mean field approximation, so on and so forth. There is another way to write the elbow, which is in this form. And this is the form that is what VAEs, and I mean, this is what we will use again and again. Okay. And so the first term here is what is called the expected reconstruction, reconstruction error. Okay. And this term here is what is called, sometimes they call it as, I mean, this is a regularization term. Regularization term. So why is this thing called expected reconstruction error? So you can think of it like this, right? So come back to our PGM. So Q phi z given x is this thing, right? This part of the thing. So you're first sampling a z using x, okay? Via Q phi z given x, this distribution. Once you obtain that z, you use this PGM to again reconstruct x, okay? So it's like you first compute the latent variable using your data, and then using this latent variable, you try to reconstruct your data. So this is why they call it this reconstruction error. So, so under this distribution, what is the how good is your reconstruction? So this is why this is called the expected reconstruction error, and this is actually a regularization term. So So this you can think that, so this what is this regularization term doing? So this regularization term is basically saying that your approximation. So remember this q phi z given x is our approximation, right? So we substituted q of z to be this thing. That is what we did in this is the variational inference approximation. This is the variational approximation that we did. So what is the regularization term? It is saying that this regularization term, this particular this particular thing should be as close to p theta of z. This is like you're saying that your so basically this is like saying that your approximation has to be well behaved with respect to your prior p theta of z. That's all. So this is like a constraint on your approximation or q phi z given x. Right? So this is like the other way, and this is how this is the form of uh, elbow that we will be using. Okay. All right. Mm. So Okay. So, again, now coming back. So, okay, we saw this. So, I mean, long story short, this is just another way to write our elbow. We know what is what the elbow is. This is just another way to write the elbow. There is no problem with it. Okay. I mean, the calculations might seem little involved, but I mean, it's not actually. But I mean, even if it does, you can just think that there's just another way to write. There is nothing extra that we did. We just uh, manipulated the terms. That's all. So, uh, yeah. Uh, Let me just see that. Uh, okay, the recording is still going on. Cool. Otherwise, I was afraid that the recording has stopped. Anyway, uh, yeah. So now let's come to the main point, right? What is our main point? So end of the day, we want to find the parameters theta and phi, and so as to maximize the elbow. So so let's write it down. So write optimization of elbow. This is what we want. So we want to. So there are two optimization two parameters. Two parameters, right? One is phi and another is theta. Phi is because of our variational approximation, and theta is your basically your generative model which you are going to use. So so basically, and what do we want to do? We want to maximize your L of theta comma phi of x, right? This is what we want to do. So of course, I mean we are going to use like let's say I mean we need to so if we are going to do some deep learning here, we need to calculate gradients, right? So uh, in any case, so what we will have to do is we will have to find what do we have to find? We have to find two things. First is gradient with respect to phi of L theta comma phi of x, and the other gradient, which is gradient with respect to theta of L of theta comma phi of x, right? If we want to do gradient ascent or something like that, we will have to find the gradient, these two gradients, right? The question is, how do we do it? Well, let's start with this phi, right? Gradient with respect to phi. So the first thing is gradient with respect to phi of L theta comma phi of x. Okay, so L theta comma phi of x. If you think, if you write, so we saw two ways to write this thing, right? One was the EM way, which was your expected value under Q phi of what log of p theta of x comma z minus log of Q phi of z given x, right? And the other way to write that we just saw was expectation under Q phi and of log p theta of x given z, right? Minus dkl of q phi and p theta of z. So these are the two ways that we can write our elbow as, right? I mean, these are the two forms of elbow. So if you see in both of these two terms, if you so I mean, yeah, if you see in both the terms have an expectation under q phi. This expectation under q phi is there. It is present in both of the forms. In no matter which form of elbow you use, there is an expectation under Q phi. Now, I mean, if you think about it, so if you take the gradient with respect to phi of L theta comma phi of x, it will result in some form of like this. So gradient with respect to phi of expectation under q phi of z given x, and there will be some term inside. Let's not worry about what the term is. Okay. Now this is problematic. Do you know why? Because so we don't know the form of this thing, right? I mean, we don't know what this q phi exactly looks like. We don't have a uh, closed form expressions for this q phi distribution. What we will do is we will basically we can only sample from this distribution in the sense that we will pass x through your network which with parameters phi and obtain z, and we will obtain multiple such z's and calculate this expectation by approximating it as 1 by n and summation of whatever the term is inside, something like that. So, but I mean, differentiation through this expectation is not clear. I mean, we cannot differentiate this expectation term with respect to phi uh, because we don't know the form of phi. We only know how to sample from phi, right? So this is the bottleneck, right? I mean, so what do I want to say is that this thing is not equal to expected value of u phi of z given x of gradient with respect to phi of whatever the term is. This is not equal to this thing because gradients and expectation don't interchange like this. I mean, generally they don't. Uh, they don't exchange like this. Uh, I mean, but we would like to. But this is desired. I mean, this is desired. I mean, if it happens, we will be very happy because once we have this thing, right? I mean, we have something like this, then we can now then resort to our Monte Carlo estimate and differentiate it and use it to back propagation and whatever. Okay. So the question is, so the question is, uh, can we can we write expectation with respect to a uh, distribution uh, that is independent of phi. Of that this is the question. So what is it? So we want to basically write something like this, right? Gradient with respect to phi of expectation of q phi of z given x. This thing is equal to, so we want something like this, so some p of epsilon of gradient with respect to phi, something like that. So this is the basically the $1 million question, that can we do something like this? So I mean, so how so and so this is what so this is where something called the solution to this problem comes as the form as in the form of something called reparameterization trick. Reparameterization reparameterization trick. So what is this reparameterization trick? Well, so okay. So let's say that q phi of z given x is equal to some Gaussian mu comma sigma, something like this. Okay. Let us say something it's something like this. Just assume for a moment. And we want to sample z from q phi z given x. We want to do this sampling. So how do you do it? I mean, the standard way to do this is via doing this thing, that z, you take z to be equal to mu. So you know that the mean is mu plus some L times epsilon, right? Where epsilon is sampled from Gaussian 0, 1, 0, I, okay? And L, so and your sigma is equal to some LL transpose, the Cholesky decomposition basically. So we know this kind of sampling techniques, right? So what is it that is happening here? So look at it. So here the problem is that, this expectation, the sampling here. So so just think of it, right? This expectation is nothing but it's a sampling problem. So how can you how can you differentiate a sampling process with respect to phi? I mean, that's not very clear, right? I mean, you will sample using some method, right? And you're saying that, well, I want to differentiate the sampling method with respect to phi. That doesn't make sense unless your sampling method itself is differentiable. So think of it here, right? Here, the z is actually a differentiable function of mu and L, isn't it? So you can calculate del z by del mu, for example, and del z by del L. And why is this possible? Because you were able to write z in terms of epsilon, where epsilon is a just a Gaussian random variable, a standard Gaussian random variable, right? I mean, essentially how we have written z here is, I mean, for example, if your phi is is actually this set mu comma L, right? Things will become very simple here because why will it become simple here? Think of it. So your expectation under Q phi, right? Q phi now is, let's say, Gaussian. So Gaussian uh, mu comma L, let's say, of any function of z, right? F of z, any function of z, right? I'm just writing this thing down, this thing here. So this is expectation under Q phi z given x of anything, f some function of z. This can be equivalently written as expected value under Gaussian 0, 1, 0 I, where and f of, you can write z as mu plus L epsilon, can't you? So, I mean, look at it. Look at the difference between the two. If I want to differentiate this thing with respect to phi, where phi is, let's say, your mu comma L, okay, this thing will result in differentiation with respect to this thing because both of them are same. And then since now the expectation here doesn't depend on phi. So what you can do is you can take this gradient directly inside, and this will result in expectation under Gaussian 0 I of gradient with respect to phi of f of mu plus L epsilon. And this essentially has answered our question, right? So what we were looking for is gradient of expectation, right? So this is our gradient of expectation is equal to expectation of gradient. This is expectation of gradient. And this is exactly what we wanted. So this is this is what we call as reparameterization trick. So basically you are saying, and this property holds with respect to Gaussian random variable, right? So, and so here what we did was, here we took a particular case, like we assumed that, your Z is actually Gaussian. We assumed that your Z is Gaussian, and hence because of Gaussianity, you can write it as this linear function of epsilon, and hence things became easier. But in general, so maybe I'll just write it down. So more generally, we can write z coming from Q phi of z given x as a deterministic 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 function of x and epsilon, parameterized 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 by phi. So what do we mean by this? So we can basically write z is equal to some g phi of x comma epsilon. In case of Gaussian random variable, that form looked like this, that z is equal to mu plus L epsilon, but it could be any differentiable function g5, okay, where epsilon is drawn from some p of epsilon, some prior distribution. In case of Gaussian, here epsilon was drawn from Gaussian 0 I, right? Which is again, this is independent of phi, because we want to get rid of the expectation here with respect to, I mean, end of the day, we want to get rid of this expectation here under with this distribution. We want to make this expectation with respect to something which is simpler, like p some anything. P, we want to make it an expectation under p epsilon, which is independent of phi. Okay. And in that case, what we can do is you can write your gradient with respect to phi of expected value of q phi of z given x of f of z as expected value of p of epsilon of gradient with respect to phi of f of g phi of x comma epsilon. That's it. So, uh, so I mean, after we have done all of this thing, what does it mean for us to write our elbow? I mean, so the elbow that we were writing, right? So L theta comma phi of x. So so we will write the elbow in a new form now, so that it is we are able to differentiate it with respect to phi. So so we will use our reparameterization trick, and we will write it as follows. So we will write it as 1 by L summation I equal to 1 to L, okay, log p theta of x comma g phi of epsilon I. So again x, right, epsilon I comma x minus ln q phi of g phi of epsilon I comma x given x, right? The whole expectation thing. And what is the other way to write it? Other way to write it is 1 by L summation uh, I equal to 1 to L uh, log of p theta of x given g phi of epsilon I comma x, okay, minus there is a dkl term q phi and p theta of z. This term is often available in closed form. Available. So for this, we won't have to do any expectation or thing. We will have a closed form solution for this thing. Well, yeah, closed form. But yeah, I mean, if it is not available in closed form, then you can do the same trick with scale divergence as well. Okay. And what you will do is, so, and what is with, well, what is this epsilon I? So this epsilon I, so all that we wrote here, these are IID from P of epsilon, some prior distribution P of epsilon. And yeah, so if you are using some stochastic gradient ascent kind of algorithm with batch size of m, so your loss function will look something like summation of x belonging to m, uh, gradient with respect to theta comma phi of L tilde of theta comma phi of x. Yeah, so this is how your loss function for this is your loss function. This is how your loss function will look like. Okay, for your I mean, with theta everything will be fine, because if you see uh, if you see, there is no expectation with respect to theta. So the gradients will just go inside because there is no reason. So there is no problem with theta. You can just take the gradients inside. But with respect to phi, there was some problem because the expectations with fair respect to q phi. And we saw that, for this q phi thing, you need to do something because you cannot differentiate the sampling process with respect to phi unless the sampling process itself is differentiable. So to make the sampling process differentiable, what we did was this reparameterization trick. For example, a simplest way to think about it is in this form of this Gaussian distribution. And this is the example that you can remember. But in general, you can make Z as some G phi. Because G phi is deterministic and differentiable, you can just substitute wherever you see Z inside your loss function with G phi of x comma epsilon, and this is how it will become. Okay. Uh, yeah, right. And this is how you will have these networks theta and phi, and then you will train all these things. Okay. So let me show how will you uh uh okay. So let us see. Okay, I mean let us come to VAs. Okay. Let us see with what are VAs. Let us finally see. So still now we have just seen uh, the build up of VAs in the sense that till now we have just seen the loss function that we need to use to learn the VAs. Let us see the actual structure and the network how it looks like. Okay. Okay. Uh, okay. So let us see. So VA is yeah. So okay. So here we have talked about two distributions, right? I mean, we have talked about parameterized distribution, the q phi z given x and p theta of x. So what do we mean by this parameterized distribution? So what does it mean to parameterize a distribution basically? Okay. So let us take one example. Okay. So let's say that you have x. So let's say x is a Bernoulli vector with you know uh, basically let's say that it's a something like this pj1 minus pj. It's a binary vector of Bernoulli trials. Okay. Binary binary vector of Bernoulli trials, something like that. So if you want to make this parametric, right, p theta of x given z, something like that. Uh, so what does it mean? So this basically means that you have a network theta, something like that, right? And at the end, let's say you have just two outputs, so something like this, right? This is your so this is all W1, I mean your usual deep learning stuff, right? So uh let's say that this is your Z, right? Your latent vector, and then you get some P output, right? So so this is basically your output, right? PJ and 1 minus PJ by the two neurons at the output layer. So in that case, your log P theta of x given Z, what will that become? That will be simply summation over J x J log P J plus 1 minus x J, right? 1 minus x J log of 1 minus PJ, something like that. Simple. Basically, you have a network that will predict. that will basically allow you to sample, that's all. Uh, so I mean, so VA is basically, I mean, you can forget this if you don't want to think about it. But VA is nothing but whatever we just saw here, where theta and phi are basically two neural networks. That's it. Okay. So what will it look like? So maybe let's say that uh, let me draw that diagrams. Okay. Uh, yeah, let me draw this diagram. So let's say you have two spaces, Z, and there is a data space and there is a latent space. So you have a latent vector here, Z, and then you have your uh, data space X, right? So you have when you have a data point X here, right? Uh, there is a encoder network which will take this. There is an encoder network that will take this and map it to your latent space, right? Something like this. It will take a X and map it to some point here using q phi z given X. Okay. And there is a decoder network here. What will the decoder network do? It will take a point from so q phi z given X. So I mean, of course, q phi z given X here is a distribution, something like that, right? It will sample from that point. What There is another network which is a decoder network which takes point from your prior distribution p theta of z, right? And it decodes, so it will take the latent vector and map it to your data point, something like this, right? It will look something like this. It is again a distribution which is p theta of x given z. Okay, and both of them are actually a network here. So this is actually a network, encoder network, which will take x as input and output. I mean, it will basically you will sample z from this network, and this is a decoder network that will take z as input and you will sample x from it. Okay, so if you want to actually think about a diagram, it looks something like this. So this is a q phi network, right? Q phi network. You will get a so it will if that takes x as input, it will give you, let's say it will give you parameters. I mean, it will give you something like mu comma sigma, let's say, okay. And then what you will do is you will do mu plus sigma raised to half epsilon, and you will call this as your z, and then you will pass this z through your decoder network, which will be your p theta, and then again this will be again some Gaussian distribution. You will get your x from it. Okay, so this is what your autoencoder will look like. Uh, yeah, so this is your autoencoding base or variational, the whole concept of variational autoencoder and or autoencoding ways base, whatever. So I mean the idea essentially is quite simple. So again, if I have to sort of summarize whatever we did today, it starts with a simple thing that it starts with your elbow first of all. Uh, then add on top of it, add the concept of variational inference, which says that, well, variational inference, you can approximate QZ with some distribution. You approximate it with Q phi Z given X. In terms of PGM, it will look something like this, where there is an inference view and there is a generative view. Now you have to learn both phi and theta in order to maximize the elbow. So how do you do that? We will do that. Okay, there are first before that we saw that there are two ways to write your elbow. One in terms of this function which is used by EM and variational inference in general. And there is another way to write it, which is what is used by VAs, which has this reconstruction error term and the regularization term. And using any of the two views, generally the second view, what we will do is we want to optimize our elbow with respect to theta and phi. With respect to theta, it's all of these things are simple because theta is inside the expectation and you can always take the gradient with respect to theta inside. However, gradient with respect to phi is something which is difficult. Why? Because there is an expectation with respect to phi. Expectation with respect to a distribution means that you will sample from the distribution first and then do a Monte Carlo approximation. However, sampling, if your parameter or the variable that you're optimizing on itself is involved in sampling, how can you like basically take this gradient inside that sampling process? So that is, so you cannot differentiate your sampling process with respect to any parameter unless the sampling process itself is differentiable. For example, and that is where this reparameterization trick comes in. And the simple way to think about it is think of how do you sample from a multivariate Gaussian distribution. You first sample from a Gaussian 0, 1 standard normal and then do a reparameterization, scale it by some sigma half and then shift it by mu. So this is exactly similar to a reparameterization trick where you are sampling Z, but the sampling process is deterministic. It is a deterministic function of the parameters mu and L, right? And using this trick, you can actually write your elbow in such a way which is more tractable, or you can easily you can easily differentiate it with respect to phi. And what VAs do is VAs basically they do nothing but whatever your phi and theta networks are, they just become a neural network. So you will have an encoder network that will take X as input, and maybe it will give you like mean and variance of a Gaussian, and then you will use reparameterization trick to shift your sample your latent variable Z. And once you have obtained Z, I mean that is how you can like encode your network. And if you want to, let's say, generate new samples, you have your prior distribution P theta of Z, because remember you have minimized the KL divergence between Q phi and P theta, right? So assuming that you have trained your model perfectly, what you can do is, so Q phi should be equal to P theta if you have trained your network properly. So what you can do is, instead of sampling from Q phi, you can sample from P theta because both of them are close or same after training. And you sample from P theta, which will be a simple distribution like Gaussian 0, 1, and pass it through your decoder network or the generator network. And it will give you a sample from, again, some P theta x given Z. And that's all. That is all your VA is. So that is why it is called encoder. First of all, the term encoder should be quite clear, autoencoder, because the X is encoded into a latent vector, and it is again decoded using your decoder network. So that is why it's called autoencoder. Why is it called variational autoencoder? Well, because it is trained using the idea of this variational inference, and the loss here comes because of this variational inference. Right. So yeah, so that's all there is to VAs. Uh, you can let me know in the group, in the teams, if there is, if something is not clear. Uh, yeah. Uh, yeah. That's all. So let's end it here, right? Uh, that's all for this lecture. We'll see you in the next lecture. Yeah. Good. Thank you, and see you.